Hello everybody, and we're back for the second part of this thing we're doing with GCSE Higher Maths revision. And we are beginning with something what we might call an essential topic, which is solving linear equations. I might move a little bit faster than the other day, but I'll try to include everything that I can into the explanation, because I appreciate that some people may not know this, and this is your chance to come at it from the beginning. Please look at the part 1 to this. There's some sort of progression, and it builds upon other skills that I'll assume you have by the time you get to this point. Okay, so let's begin. Rearranging equations where the unknown is on the denominator. Now, this is something of a pain, and I'm not going to go through basic solving equations. It's just where these two in particular are where we have them on the denominator that cause an issue because people don't know how to deal with them. You're not used to moving an h over because it doesn't look like you've made any progress. But that's exactly what we're going to do. Your number one rule is to get rid of the denominator. We'll call that focus on the denominator. So multiply both sides by h, and you'll see 72 equals 4h. Doesn't feel like progress, but now we're going to divide by 4 on both sides, and that's going to be 18. Now, there is a trick. Let's call it a over b equals a number, like c. If you wanted to rearrange, and let's say b is the thing that you want to isolate, then you can switch b with c. So a over c equals b. You see, I'll just show you visually that b and c switched places. And that's perfectly fine. It's a trick. It's worth using if you want to save yourself some time. Okay, let's keep going. I don't expect anyone to be on the live, so I won't be checking too often for questions. I'm aware that the time of this is not the weekend, and so it's, what is it there? It's 11, 12, midday. So this will be for all of you when you finish this the day. You can double check your answers and chime in. Don't forget, if you have any questions, you can send them through to Patreon or in the comments section of this video. Okay, so we looked at equations, the algebraic equations the other day. Not much to be said about this except what we might do to get it on like together, and probably the best way is a common denominator here. So we want to solve this by finding that common denominator. Now I'm going to put it in brackets because when we don't know x, the common denominator is multiplying them together, and we don't know what x is again, and so we have to leave it as an algebraic expression. And that's easiest if we take note of these things like x plus 1 and x plus 2 as specific items. And we put a bracket around it so it's clearer to see the differences. So x plus 1, x plus 2, that's going to be the common denominator. And somebody thinking, that is a big leap. Well, maybe, but I'll show you real quick. If it was 2 over 3 plus 4 over 7, and you didn't know what 3 and 7 went into, if you do 3 times 7, that's the quickest way to find a number they both go into, which is 21, but you can leave it as 3 times 7. And here we don't know what x plus 1 and x plus 2 go into without knowing what x is, and so we just leave it as x plus 1 times x plus 2, and that is the common denominator that we're aiming for. Now, if x plus 1 is already on the bottom on the left-hand side, we're multiplying it by x plus 2, And if we do that on the bottom, it needs to happen on the top as well. So the 4 also gets multiplied by x plus 2. And on the right-hand side, if we're multiplying by x plus 1 to get the denominator we want, we have to do that on the top. Okay, getting there. And not so straightforward, this question. It's a bit longer than we imagined, but we're here for it. X plus 1, x plus 2. And now we could expand these denominators separately. So we're going to get 4x plus 8 on the left and 5x plus 1. And they are being added together. And therefore, we have a total of 9x plus 9. Okay. Interesting. We can actually factorize 9x plus 9 if the 9 comes out. So we'll do that again at the side so we're not getting too confused. Then we get x plus 1. So let's do that instead. 9x plus 1. And I saw that might be the case. We can sort of cancel this, and therefore that makes our life a lot easier. Yeah, just thinking about that, cancelling it, so whatever it is, yeah, that's fine. Okay, and therefore, well, remember that's still equal to 2, but now we have 9 over x plus 2 equals 2. And then we multiply. Now this is again the denominator on the bottom. And we need to be brave here. This is the methodology. We're going to multiply by that denominator, as was recommended in the previous one, because you want to get rid of the fraction first. So if we multiply both sides by x plus 2, we get 9 equals 2 lots of x plus 2. And then, it doesn't feel like we made progress, but we did. We're going to expand the brackets. We're going to move that 4 over, so take away 4 from both sides. And then divide both sides by 2, so we get 5 over 2. And that's perfectly fine for an answer, or 2.5. Yeah, we're good. Just trying to find my mouse. Scroll down there. Okay, now back to the 7x minus 3 equals 60. We've got 7x plus 3 to both sides equals 63. Not too bad. Divide both sides by 7, and we get 9. Cool. Solving this one, most people go straight for this. They take away 5 from both sides. They times it by 4. I did a video where I take a question a lot like this and I start with different operations to help, well, to hopefully I'll give you the confidence to say, I can try something and see what happens. And really you can't go wrong. As long as you're applying the same thing to both sides, you can't go wrong. So, I mean, let's do something I wouldn't consider a good thing to do, which was target the plus 5 and say, let's take away 5 from both sides. Because x plus 5 over 4 minus 1 minus 5 equals 1. And that would therefore be minus 6. We're actually not any further along because taking 5 from both sides will not affect the target. It does not affect this. It would affect the minus 1. So honestly, this is the best way to start. I could times everything by 4, as long as I remember to multiply everything by 4, including the minus 1 there. And that leads us to something pretty cool as well. The best way to start this question is to deal with the negative 1. So x plus 5 all over 4 equals 7. Then we're going to multiply both sides by 4. And then we're going to take away 5. There we go. X over 4. Yep, well, there's a lot of language around this, but it means divide, doesn't it? So to get rid of a denominator, to get rid of a division, we multiply both sides by 4. And so we get x equals 120. Here's where we have 2 x's. Now, the best thing to do is to think about what will keep it things positive. So if I took away 10x from both sides, like over here, that would bring things into the negative. So the best thing is to take away 7x from both sides. And that would lead us to have 3 equals 3x minus 6. And then we're going to add 6 to both sides. And then we're going to divide both sides by 3. And then we get x equals 3. And it doesn't matter if it's the 3 equals x, it's the same deal. I'm pretty sure you're okay with that. Okay, and finally, this is where we're going to expand brackets twice. And then it requires us to simplify. We have x's in 2 places. But if we expand these brackets, I'm just going to write it a bit more clearly. Then we can combine. Now we're going to be careful because this is a negative 3, right? So negative 3, that becomes negative 9x. And then plus 30. Like that. And now we've got some like terms, the x's. So, and we've got the numbers as well. However you want to highlight these. 30 take away 12 is 18. Let's write that out the front. Still positive. And then 8x minus 9x is minus x. This is another issue. This is why this question is here. When it's a negative x, people often don't know really what to do with it. There's 2 ways you can deal with this. The first is we're going to add x to both sides. People don't often do this because they feel like they're not getting anywhere. But now you can see x is positive. Life is a bit easier. We'll take away 11 from both sides. And we get x equals 7. The other way of dealing with it is to take away 18 from both sides. I guess people like to work left to right when they read this. So if we take away 18 from both sides, we've got negative x equals negative 7. And here's the bit they don't like. It's like, well, these sticking out negative bits. Well, you multiply both sides by minus 1. That's one option. Or you could divide both sides by minus 1 because the effect is absolutely the same. And the reason why we can do that is this is essentially minus 1 times the x, or we could call it like this, minus 1 on the bottom. And it's just a way the cookie crumbles. So let's multiply both sides by minus 1 and we get x equals 7. And that's confirmed on both methods. You pick which one you like best, and good luck with it. Okay, a lovely looking one. Just have a quick look at every question and perhaps think if there's a different way. That could be tackled. And before you start it, it won't be awful. So we'll go through a number of different ways here, like in our journey, number of common mistakes that we might make doing this. And it looks like a doozy, looks like a good one. So let's see how we can do this. I'm going to first of all, this is just my preference. As I said, I do all of these questions fresh with you on here, and so we see how it goes. What I'm attempting to do is make the right ones positive. Like I can add together these two. If I'm going to try and find a common denominator of them two, you're going to find that really hard. It's possible. It is possible by multiplying them together, but I just got a feeling that this is an easier way of doing it. I've moved this over to the other side and this to the right. And now I need a common denominator. So that's going to be this. 1 over x plus 1. It's probably unnecessary. I'm sure the common denominator will be fine. It's just that it's x plus 1, which maybe this way is better, maybe it's not, we'll see. 3x, and then 3 minus 2 is 1. So this is kind of groovy. When we have the things equal like this, like the whole format's the same. It's 1 over something and 1 over something. That means that this is equal to this. Okay, so x plus 1 is equal to 3x. Because everything else is the same except those two. And how do we figure this one now? We're going to take away x from both sides. And then x equals a half. And before we move on from these calculations of solving stuff, how would you check that these are correct? All right, so you want to double check, oh, is this correct? I can't just write it. I want to make sure I feel confident. You're going to put it back in here, and you're going to see that the left-hand side will equal the right-hand side. Okay, I'm not going to do that now. I'm just going to move on to our next question. Substitution. You may have noticed there are some what you might consider simple topics in here. These are literally the ones that people forget in the heat of the moment. There are 5. After about 6 years of research, I found that there are 5 topics that are commonly full of misconceptions that people get wrong. One of them is substitution of negative numbers, but it's so important that we need to just make sure we get it. But a lot of problems happen here. Right, let's go. There's obviously strategies here. My first recommendation I recommend so many times is add brackets wherever possible. So I'm going to be putting B and C in. They're going to be replaced, so I'm just going to write it as big as I want to feel comfortable. 4 times something, take away 6 times something, and that's all squared. So you can see I've got this bracket open where I'm going to put something in. So the first bracket was B, so B is 2. Substitution means you're switching for something equivalent. So B, I'm going to switch it out for what it's equal to, which is 2. And then the C is 4. Okay, now it's just a matter of BIDMAS. So we're going to do what's in the bracket first, and then we're going to do the multiplication before the subtraction. So it's 8 subtract 24. And that's going to be squared. I'm going to move over to the right now. 8 take away 24 is negative 16 squared. Thankfully, everything squared is positive, but I want to make sure you're doing this right in the calculator. Don't forget that negative 16 squared, if you put that in a calculator, they may square the 16 and then make it negative. What you want is negative 16 in the brackets squared. So make sure you do that. Some calculators are pretty good at doing that automatically. It's a common thing. But just make sure you know which one works for you. And therefore we end up with 256. Let's get that out of the way. There you have it. Okay, evaluate this next one. So 6D, let's avoid the brackets this time. Let's see if it works for us. Is it neat enough? D is 6. So wherever you see a D, you're going to just write 6. And you notice that I've added structure. I've added a multiplication here, so it's clear when it comes to the BIDMAS phase. I'll keep this bracket. 5 times negative 5 squared. Okay, let's do things a bit at a time. 36, take away. Do the brackets. Positive times a negative here. Okay, so we've got 36 take away, and that's going to be a positive result, but we're still subtracting it. So it's 625. I guess we can do this. And 36 take away that is negative 589. Now the numbers are big and ugly just because it forces you to focus on the method. Okay, so numbers aren't always nice like that, remember? Okay, what is the third? Pi r squared h. Do you remember what this formula is? It's the volume of a cone. So it's always a third of the cylinder that surrounds it. I love that fact. Weirdest random thing in the universe. Well, one of. Okay, let's put these in. Fractions are involved this time, so let's write them properly. Multiplied by pi, multiplied by r, which is 7 over 2 squared, multiplied by h, which is root 3. Yeah, so where do we go from here? So, well, we have to evaluate it, and you can write it in terms of pi, I suppose, but let's take it a bit at a time. 49 over 4 times root 3. And we've got the two fractions we can handle now. Pi and the root, a little bit separate. So we're going to do the fractions. 49 over 12. Just multiply the top, multiply the bottom. Pi root 3. Now that would be our exact answer. You can leave it like that. But we're going to put it in a calculator and see what we get. Root 3. So as a decimal, this thing is 22.219042, etc. And we can round that to something sensible, like 22.2 to 1 decimal place. All right. Captain Fantastic. There's a couple of things I need to adjust. There we go. Okay. Find the value of a, where a is equal to this. Now, do you recognize this? This is the cosine rule. Yes. But we've got rid of a squared and we made it a. Okay, so a equals big square root. Okay, give us plenty of space. 7.1 squared plus 8.9 squared, take away. This is where I actually put this in another bracket. 2 times b, which is 7.1, times c, which is 8.9, multiplied by cosine. See how long that needed to be, eh? Multiplied by cosine of 62. Alright, so this is the brackets enough to make it clear. And what we're looking for is a calculator to be in degree mode. So you should see a little D symbol at the top of the calculator. And that is essential here, because we're using cosine, which is trigonometry. So we're going to need that to be correct. Otherwise we'll get the wrong values. So we can do these in a couple of stages. The problem here is that some of these numbers aren't very nice. Like, you wouldn't want to write them out. So the best we can do is an intermediate stage. That wasn't too bad. And neither is this one. And we could probably do 2 times 7.1 times 8.9. Which is 126.38 times cosine 62, which I know is going to be not that nice. So we've already made it a little bit more simple, and this is where we can put it in the calculator. So I would square root 50.41, 79.21, subtract open bracket, literally writing what I have, 126.38 multiplied by cosine 62. Now I have to close all the brackets I've opened. Otherwise you get an error actually. So I got 8.383. It doesn't say what we round it to, but in the case where it doesn't, just do it to something sensible equals 8.4 to 1 decimal place. Because I lose all the others are to 1 decimal place. So we'll just go with that. Okay, lastly, evaluate AB minus 555C, where this is, oh, lovely. So this is testing not decimals this time, but surds. Yippee. So A times B, A is 4 root 8. I'm going to put this into brackets. Multiplied by B, which is 7 root 12. Take away 55, what? Multiplied by 2 root 6. It's better be good by the time. So we have to evaluate this. So we have to see what it is as a value. Currently it's still an expression. So 4 times 7 is 28. And root 8 times root 12 is root 96. I'll leave it like that for now. We'll see how it goes. 55 times 2 is 110 root 6. So I don't know if your creative mind is thinking the same as me, but I'm thinking that this 96 might have a factor of 6. Because this is pretty much as low as it can get. It's very simplified. This one is very probably not quite simplified yet. 6 does go into 96, doesn't it? If you think about 60 and 36, that adds up to 96. So it goes in 10 plus 6 times, so 16. So this can be written as 28 root 16 root 6. And because 16 is a square number, that can be further simplified to 4. 28 times 4 times root 6. Take away 110 root 6. And the finale, 28 times, well, it's not quite the finale, is it? 112 root 6. Take away 110 root 6. Well, that's just 2 root 6. That's actually a pretty sweet question. It's nice when the numbers work out to something whole. It gives you confidence, but you shouldn't hold on to it. Really, what we need to tackle, I think, if we're honest with ourselves, those moments where we don't know what to do next, where the numbers are not speaking to us, and we need to remain confident. That's going to be 60% of your grade if you can do that. All right, let's go. No time like now, eh? Okay, so 2D and 3D Pythagoras. So this is an example of 2D Pythagoras. It's actually a composite sort of diagram where we have different sections, and we're going to have to make our way across. So find AC. So we can highlight AC here. So this length. We don't know enough about this triangle. Pythagoras is a squared plus b squared equals c squared, where a and b are the small sides. And when you have diagrams like this, the best place to start is where you have most of your information. So most of your information comes from this triangle over here. Firstly, we'll label it. So let's call it 1. And the calculation for 1 is going to be the small side and the small side again squared. Square rooted, I'm sorry if that's too fast, but I'm writing it as AD squared, right? So that's AD squared, but if I square root both sides, I find AD, which is what I want. And there is a quick way of doing it, like you just jump straight to the square root when you write it. And not too bad. So what does this look like on a calculator? So we can actually work with the thing. So 14 squared. Actually, let me square root first. 14 squared plus 10.5 squared. Lovely. And that's 17.5. It's really nice that we don't need to leave it in some exact form, because I don't want to write that out again if it's too many decimals. Right now we know this line is 17.5, and you could write it on there, but it could also make it messy. We're going to write it on there, why not? So question part number 2 is this second triangle, because we now have 2 bits of information. We've got the 42, which is a small side, and we have the 17.5, which is a small side. And if we square root them after adding them together, we're going to find AC, and that's what we're looking for in the question. So let's go ahead and do it. Moment of truth. 42 squared plus 17.5 squared is wholesome 45.5. Now this is united. If that's a word, it's got units. Okay, so let's write them. Centimeters. Next, that's 2D Pythagoras. Okay, now this is 3D Pythagoras. In the diagram below, find the diagonal length GA. So where's G? There's G. There's A. So it's like a line that goes straight down here. All right. That length does create a right triangle. If we look at it like this. So this is the base. Now I think the best way of visualizing this, oh dear, this is a bit of an angle. The best way of visualizing this is if we think about it as a room. Okay, so this box is a 3D room. If you start at G and you attach a string to A, that's the line. Where's the right triangle? Well, keeping parallel with the baseline, we're going to draw a right angle line in there, and hopefully you can see it. We don't have many dimensions for this. If this is triangle 1, okay, this triangle can be written flat for us so we can focus on what we're doing. We do know the height of the triangle is √3, but we don't know the base, which is E to G. Okay, we don't know enough about this triangle. So we need to figure out what is linked to EG at the bottom, and that's going to be this triangle here. Okay, so we're going to call that triangle 2. Triangle 2 y los lares. Okay. Now what do we know about that triangle that's lying flat on the ground there? Well, it's got a base of 10, as you can see from there, and it has a height of 6.9. Now we're just going to check if they've tricked us. I wrote these questions. I don't know why I say they, it's a habit. Centimeter, centimeter, centimeter. So yeah, good. No conversion needed. So we can actually find EG using this second one. So Pythagoras, as usual, 6.9 squared plus 10 squared square rooted equals EG. Is that correct? Yeah. Let's do it. $12.149 blah blah blah. I'm going to keep that on my calculator because I'm not writing that out again. So now we know that EG is 12.149, but it's on my calculator. We could do our final calculation to find AG, and that's going to be √3 squared. See, that's brilliant. When you square a square root, it just disappears. Do that without a calculator. Plus 12.149. Got it on my calculator still. ... Square rooted equals AG. Okay, so then finally, let me put that on a calculator. Answer squared plus, and I know that square root of 3 squared is just 3, so I'm going to write answer squared plus 3. So AG is 12.2723. Does it say the accuracy? Nope. So I'm going to go for 12.3, and it's in centimeters to 1 decimal place. I believe it's, yeah, centimeters. Okay, lovely. That'll do us. So that's 2D and 3D Pythagoras. What's the difference between the two? Not much. In this one, we're using the same algebra as we are down here. and there's the same triangles appearing. The only difference is you have to try and visualize that triangle in a 3D shape. The very common shapes that they use them in. Another one would be the Saturday morning tonic question I made, where you had a button. There's obviously one at the side there, but if you split that, there's another one up there. So it's being able to see them in 3D, but then once you've identified them, just draw them again. Please, please, draw them again. And then they become ordinary works. So don't be afraid of the big bad 3D. Okay, let's go up. So once we've done with right angle triangles that have these sides, we're now going to be looking at the sine, cosine, and tangent rules. These are ones that allow us to work with more complicated triangles and non-right triangles. So this first one, it's definitely full of right angle triangles. We have less information than we'd like, but we can work there. So we're trying to find angle DEB. Where is that? DEB. Right there, that's the focus. Call it theta. We don't have anything on that triangle except the 7. If we had two sides, we could find the angle. So what we're looking for really is to find two sides. We can do that. We've got an overall actually. Just looking at all the information we have. Like if you just focused on this overall triangle, you could find any of the other sides you wanted, but that's not really going to help. Okay, so I'm going to focus on this triangle here because I've got two pieces of information. What does that allow me to find? Actually, I might need to use the overall, because if I focus on the triangle with the most information, which is that one I just highlighted, I can only find one of the sides. So I will focus there, but if this is 22 degrees, focus on that triangle AEC. If this is 22 degrees and that's 90 down there, that gives 112, which is 68. I don't know if this is useful, but I just write it because you never know. Okay, so focusing on number 1, and you know, it's okay to write this out again. If you want to label stuff. And I'm thinking that we can go for the bottom. So that's D and that's C, and I want to find that bottom. So let me call that one up there. This would be the opposite. It's the opposite because it's opposite the angle that we know. Okay, so it's opposite there. The hypotenuse is the longest one. It's opposite the right angle. And then the last one is just the adjacent, and that's what we're looking for. That's the unknown. So we can give it a letter, but I'm just going to call it DC. Put it in brackets. Now with SOHCAHTOA, we remember this phrase because it tells us the formulas, okay, the ratios. Now the formula that we're interested in here involves opposite and adjacent, so it's tangent. So tan of the angle is equal to the opposite over the adjacent. I was thinking about putting the numbers in there, but no, not yet. So the angle is 22, so tan 22, make sure your calculator is in degrees mode, is equal to opposite, which is 7, over the adjacent, which is unknown. Call it DC. Now do you remember that little trick earlier where he said if we have a fraction equal to a number, we can just switch these two in order to rearrange? I would be doing that one if I were you. So DC equals 7 over tan 22. This question is far from over by the looks of it. But let's see what that turns out to be. I've seen a lot of mistakes here. I actually put my tan 22 in brackets. I'll close 2 of them. because I'm going to be in control of what my calculator processes. 17.325, 60, etc. Okay, so we're going to leave that on the calculator ready. But what we found is the bottom, 17.325 ... In fact, I'm not going to keep that on a calculator, because I know that to find I'm aiming to find ED, so I'm going to have to find the overall and subtract the 17. So I'm going to write as many decimal places as I can so that I don't need to recalculate that later. Actually, it's not too bad. I could just put that in the calculator. But whatever. Now we're going to focus on the overall triangle. I'm not going to give it a number because it's hard to see. I'm just going to give it the labels that are its vertices and fill in the details I know. So I've got 22 this time. I've got 10 up here. And my aim would be to find again the bottom. So this is a repeat of the previous. We're finding EC, which is the adjacent. That's the opposite. So we're dealing with tan again. So tan 22 equals 10 over EC. So EC equals 10 over tan 22. So instead of 7 over, it's 10 over. So EC is 24.7508. So we can keep that on the calculator. And we can subtract, open bracket, 7 divided by, yeah, I'm going to write it again. Why not? Tan 22. So E to D is the 24.75, take away the 17.325, so ED equals 7.4256. See, this question is a good one. Now let's finalize this with our information. We know that in this little triangle EDB, the bottom is 7.42, etc. Keeping it on my calculator. This top is 7, and this is the unknown theta. So to this theta, this is the opposite. This is the adjacent. So again, it's tan theta, that's the unknown this time, is equal to the opposite, 7, over the adjacent, which is 7.42, etc. Now that number we can find. So 7 divided by answer. We'll continue here. We've got tan theta equals 0.942727, etc. That's if I do 7 divided by 7.42. We don't want tan theta, we want theta. So to get rid of the tan, we have to apply tan to the -1 on both sides. What that does is get rid of the tan. It's an inverse, you see. So theta equals inverse tan of that. So shift tan is how you get to the inverse. I'm going to click answer because I kept it in the answer. 43.3139 ... degrees, because this is an angle. Does it say the... No, it just says find it. So we're going to write it as 43.3 degrees to 1 decimal place. And there you have it. We're drawing into a late sort of an evening, and I'm going to call this next question the last one, and we'll continue in session 3. We made good headway, so I think session 3 will probably be our last one. This is available on Patreon, so go grab it. We've got a bit of probability. We've got a bit of 3D. In fact, these last pages are just a few of these things. Let's take the time to look at them. A weekly planner. If you've not done your revision plan, it's only meant to be rough. What subjects are you doing at any given time? You can print that out and use it. So actually, kind of cool. We're near the end. And my favorite, probability, is on its way. So last question. In the diagram below, calculate the length AB. Okay, we can do that. So let's focus. There's AB. You'll notice that none of these are right angle triangles. That means that we're going to be using more advanced methods, either the sine rule or the cosine rule. And I can tell you right now that, well, let's get to it. How do we start this question? I want to get to here. Is there enough information in this question? You're probably thinking no. Let's look at this triangle then. Well, we've got a side and an angle. And what would be, well, what could we find about the other triangle using this triangle? Probably this length that it shares, right? AC. Now I can tell you, that's what I was wanting to tell you earlier, that if all three sides are involved in a triangle, non-right triangle, and you have the angle that is opposite the unknown, this is classic cosine rule. Okay, so number one is going to be cosine rule, and we're going to set this up in such a way that we can do it. So A, and we're going to be finding little a, and we'll call that B. We don't need to use the labels they give us, but funny enough, that is going to be C, and little b. Now this is one way of doing it, but I wouldn't necessarily think you need to do it all the time, label it your own way. You just need to remember the structure of the formula. But it's essentially a squared equals then the other two squared and added together. It's kind of like Pythagoras at this stage. Take away two lots of those two again, see B and C, and the only time the A comes back is at the end, with the capital A with the angle. And we're trying to find A squared. So we actually did a bit of substitution earlier this live stream on this particular equation. So things should be okay for us. A equals the square root of, no, don't do that, B squared, which is 11 squared, plus C squared, 12.5 squared. Take away 2 times 11 times 12.5. And you see what I mean about these numbers? They're being used twice. So you don't need to like look for them. They're literally here. Times cosine of the angle, which is 47. And if you don't mind, I'm going to put that all in a calculator now. All you have to do is be careful with your brackets, okay? And we get 9.47103. Yeah, etc. This is not the final answer, so we don't need to write it rounded at this stage, but we're going to carry on with it in the calculator. Hopefully it's going to be good for us. Okay, so the next triangle, which is up here, triangle number 2, we might want to write it out again. We're aiming to find that top length. So let's get rid of these labels. They weren't 100% necessary when you get good at the method. This is 9.47. Always use the full number until the end. That's why I write the ... Okay, let's label what we got. 71, 34, And we have the opposite there, which is 9.47, etc. And we want to find this one here, x. So this is classic sine rule, and I'll tell you why. Sine rule is dependent on pairs. So we have a pair of information here and here. And although we don't know one of them, this is still a pair of information here. And out of those two pairs, one thing is unknown. That is sine rule. Okay, so for this one, sine rule is a over, depending on whether you're finding a side or an angle, but this is one way of writing the formula. And you only ever need two of these, so I don't write the C as well. It doesn't matter how you label this, really. You can, as long as you're thinking about it in terms of pairs, it doesn't matter which one's A, which one's B. But if you're really worried about it, then make that one A, make that one B, and you can see that it's just the pairs that go together. With an unknown side of x, so it's x, let's say A is there, x is paired with sine 71, and B would be 9.47, which is still in my calculator, all over sine 34. And we'll just do a bit of rearranging. We'll get rid of this fraction so that we get x is equal to sine 71 times 9.47 all over sine 34. Now, do you know what someone in my class did today? They did sine, I didn't do this question, but it was similar, 71 times 9.47. And they said, oh, I got it wrong. What have I done wrong? Help me. I was like, well, I'm sure you didn't put it in the calculator wrong, but actually they did. The calculator starts to open a bracket when you write sine, just like this. And if you don't close that bracket, wow, if you don't close that bracket like this, then what you're going to do is sine of a really big number. All right, you see that? It's going to be sine of, I don't know, like 630. Well, you're really looking for sine 71, then times 9.47, etc. All right, it's still in my calculator, that number. So 9.471 multiplied by sine 71 is 8.9 divided by sine 34. X is 16. Oh, I think the program is opening in the background that I didn't want to open. Give me a second. That's better. Hopefully that didn't affect anything. All right. 16.01 421 767. It's in centimeters. Let's do it. 0.1 centimeters to decimal places. All right. Where's my mouse? Yeah, so we've now at a stage where I said we'd do that last one, but we've got 4 minutes to the hour, and let's see if we can sort of get this in while we're still using cosine and tan and all that stuff. So there are certain values of trigonometry that we should just memorize, okay? So just really briefly, the cosine graph starts at 0 degrees up at 1, and by 90 it's down at 0. Okay, so I know that cosine of 90 is 0, and you can verify that and by putting it into a calculator, and you'll find that that's true. But it's one of those ones you can memorize. Interesting. Let's go for a few. So cosine of 0, Cosine with a degree of 0 equals 1, because it starts life up at 1. By the time it gets down to the axis, it's 90 degrees. So cosine of 90 is 0. So those are two important ones. With sine, it's the other way around. So it begins at the origin. So sine of 0 degrees equals 0. And by the time we get to 90 degrees, sine of 90 is 1. And they work in, like, they're very similar graphs, just shifted. So that's worthwhile to know and make notes. Tan 45 is a little bit different now. How would you find tan 45 if you didn't have a calculator? Because remember, this is without using a calculator. This is an exact value. There are two really important triangles. One of them is the isosceles unit triangle, and the other is the equilateral unit triangle. And tan 45 is going to come from a triangle that has 45 degrees in it naturally. And that particular triangle is going to be the isosceles. So we'll draw it here quickly. There we go. Isosceles right triangle. So if this is 90 and this is 1 and this is 1, then these two angles here must be 45. Right? It's a very special triangle. If you have a right angle triangle and both of those lengths are 1, it makes it isosceles like this. And we can know every angle and every side on this triangle because we can use Pythagoras, right? So 1 squared plus 1 squared square rooted equals root 2. And so the hypotenuse is root 2. We know everything about this triangle. That allows us to perform like trigonometry on it to find out tan 45. Now remembering that tan is equal to the opposite over the adjacent. So as long as we can find a specific angle with 45, so let's make that more like tan theta. We found the angle 45. This is going to be our focus angle. The opposite is here, that's 1, over the adjacent, which is here. Right? So that's also 1. So tan 45 equals 1. You can verify that on a calculator. But if you didn't have one, like in this question, this is how you do it. You refer to your triangles with which you can draw everything on them. The other one, by the way, is the unit equilateral, where you have sides 1, 1, 1, and that's all 60, 60, and 60. But how do we get the right angled element to this? We split it down the middle. So in fact, the triangle is half of a unit equilateral, where we have 1, and actually a lot of people like to use 2 as the side of the equilateral, but we'll use 1 for now. If this drops down the middle, then that's going to make this a half. Let's get rid of that for now. This remains 60 degrees. This became 90, and this is half of what it was before. So we've got all the angles. We now need to the final side, which is going to be 1 squared. Take away a half squared square rooted. So let's just do this properly. 1 minus a quarter, which is 3/4 square rooted, which is root 3 over 2. So we know everything about that triangle. What are the angles involved in these two triangles that we know everything about? 45 degrees, 60 degrees, and 30. So whenever you're asked to do trigonometry and you don't have a calculator, you need one of those 3 angles, and you can find their exact value. Should we look back at the question? Have we done it? Oh, yeah, we've done it. We've gone extra, but that's fine. We get rid of this because it didn't pertain to the question. I'll leave it like that and conclude that it equals 1. Nice, and not a calculator was disturbed. All right, thank you everyone for coming along. I can see quite a few people have viewed during this session. I didn't expect anyone, thanks to the time. But hopefully people watch it in their own time, and people tend to. Have a look at some of these and question anything you want. Tomorrow we'll go through the final ones, which are 3D trigonometry and probability, which is my favorite, which will look at tree diagrams and Venn diagrams with probability notation. So that's going to be super fun. And I'll see you there. Good night, good morning, or whatever it is for you. Have a good one.